Hey everyone, Dr. Calkins, last installment of a big chapter, week 13, chapter 2. The thing that we haven't mentioned that we should is how to do conversions. I like to do conversions of temperature first because it shows you the overall process that we're going to see throughout the next and remaining 4 chapters, this one included, for exam 5 and then the final exam. So in temperature conversions, what we need is to understand where do conversions come from and then how to set them up and cancel units. That's really what we have left in this semester, just with moles in the next 3 chapters. So if we have a thermometer, the first one that was created was by Daniel Fahrenheit. And what's important about his is it was pretty obscure, and that's why they changed it. He's using temperatures that he thought was easy to manipulate. So what that means is he chose a temperature that he thought other people around the world could use and make their own thermometer through his kind of instructions. So when he picked a temperature, he thought, let's put salt into ice. That'd be a cold temperature that anybody could produce around the world. And unfortunately, what we realize for salted ice is it's enough to freeze ice cream, which is ironic that we throw it on to ice and have it try to melt, but that's a different chapter in 2 weeks. So unfortunately, when water really freezes, which is our comparison, it's going to be at a positive 32 degrees. His number for 0 was salted ice, which is 0 Fahrenheit. We're using 32 Fahrenheit so that we can compare this thermometer to a couple more and do conversions through them. What we also need to know then is when water boils. So if you know that, great. If you don't, you're going to get it for free, and that's 212 degrees Fahrenheit. So 212 and 32. What's important about that is this spans 180 degrees, which means there's lots of marks on this potential cartoon thermometer. So 212 to 32, 180 is the important part. This is the boiling point and the freezing point or melting point of water. So because these numbers were kind of weird, his 100, just for historical context, was his armpit. He may have had a fever. He called it 100. We kind of use 98.6 nowadays, but that's where 0 and 100 were. This is just where water happens to fall in that scenario. So a little bit later, I think this guy was Swedish, came up with an easier idea with less markings, but easier to think about. He just said, let's just call it 0 and 100, because that's easier and less kind of unique compared to 212 and 32. This was Anders Celsius. So what's unique about this is it's easy. 0 to 100 is a whole lot easier to remember than 32 and 212. The reason the United States is the only country still using Fahrenheit is because it is much more precise in the sense that, or in this case we could say accuracy because it's more exact. It's a better definition. It's got more markings. It's got 180, where Celsius, which is what everybody else uses, is only 100 degrees between the melting points and boiling points of water. So ours is almost twice as exact, and that's why we've kept it. Nobody else cares about exactness. Apparently, they just care about what's easy. So we had Daniel Fahrenheit, he had Anders Celsius coming up with these thermometers. And then lastly, what we have is this new thermometer created a little bit later by Kelvin. Ironically, the creator was named William Thomson for the Kelvin scale, but he was rich and he was English and he had a title, and his name was Lord Kelvin, so that was where that came from. He wanted to make sure there was no negative temperatures possible, so he started temperature scales in this situation with 273 K, that's not degrees, it's just K, and then 373. And the reason he did that is because the lowest possible temperature was absolute 0, which is 0 K. If we were to convert that to Celsius, because it's offset by 273, this would just be negative 273 Celsius. And if we wanted the coldest temperature possible in Fahrenheit, that would be about negative 460 roughly. It's not quite there, but if we round up, it would be negative 460 degrees Fahrenheit. So there's the coldest possible temperatures that exist. So as we look for some conversions, we just need to use the information that we have. Notice this is still 100 because it's the same scale, just offset by 273. we need to be able to jump back and forth between these temperatures. So let's say we go to Mexico or to Canada on vacation, we think we have a fever. What would a fever look like in that situation? So if we know that a 96.8 degree Fahrenheit temperature would be something that's normal, whoops, 98.6, I said it right, just wrote it wrong. What would that look like in Fahrenheit? Well, as we compare the scales, we have to think, what's the major difference? Well, one of the major differences is one's at 32, one's at 0. So would it make more sense now to correct for the 32, or should we convert to Celsius, then correct? The problem is, if we were to convert to Celsius now, we'd have Celsius, there'd be no way to subtract 32 Fahrenheit once we're in Celsius. So it's important, and this is the number that can change in your homework, if we have a number in Fahrenheit, like 98.6 written correctly, we would want to subtract 32 degrees Fahrenheit now, because notice they're in the same unit. Units are very important. They need to be able to cancel. And to cancel, what we need is a conversion factor. So as we get a conversion factor for temperature, we need to make sure, and this is the single most important feature of the remaining chapters of the semester, if we have Fahrenheit in this numerator, we're going to need them in the denominator in order to cancel. That has to happen in every problem that we do from now into the rest of the semester. The unit that survives sits on top in the numerator, and what we have here is Celsius and Fahrenheit. We just need some relationship, and this is where we could use the metric table, we could use the English to metric conversions we were given in the other lecture. Here we just need to use the information that we already provided over here. For every 180, Celsius spans 100. So for every 180, Celsius spans 100. This is our conversion factor, and that's what we need in order to answer a problem like this. Just remember that in your calculator you're going to need to use parentheses. PEMDAS says P first. Otherwise, things like this, you're going to multiply 32, do the conversion, and then subtract, and that's not what we want. So in a calculator we could type 98.6, subtract 32. So our calculator needs to do that first, otherwise it's going to take 32 and convert and then subtract, and that's not what we want. And then we can multiply, and then you can do the 180 on bottom, whoops, 100 divided by 180, and you get 37. So what's important about 37 is that's what normal is at the hospital for any country other than ours. What's unique about this one is it's in the tens place. Because this is an exact conversion, we're looking for this to stay in the tens place. So you're missing that 0.0 that would be important there, and that would be in Celsius. So 3 sig figs. Notice we have 3 sig figs in this starting number, so make sure you maintain that kind of idea. So let's check our work. Let's make sure we can go backwards. So if this is truly the conversion, let's try it in reverse. 37.0 Celsius. We need to go back to Fahrenheit, so we need to reverse this. Would it be important now to add 32 or to convert? Well, if you think about it, if we add 32, Fahrenheit and Celsius are in different scales, that wouldn't make sense to add any number that has different units. So much like before, we need to do the conversion factor first, and we need Celsius to cancel on the bottom. This is the single most important feature of the rest of the semester, that you can do this process. So you put Fahrenheit on top, and then you look at our scale and say, well, that's just 100 versus 180, but now the 180 is on top and the 100 is on bottom. You might see in the textbook that they say 9/5 or 5/9, they just reduce those by 20. Once we do this, we get to Fahrenheit. We need to now add 32 so that we can correct back up from 0 on our other scale. We can only do this because we're now in Fahrenheit, so now we can add Fahrenheit, and you're going to get 98.6 exactly, which is what we want. If you want to convert to Kelvin, a little bit easier. You take your Celsius temperature and you add 273. So in your calculator, you're going to get what, 310. And be sure that that 0 matters, because if you're doing addition, we need to stay within that ones place in this situation. Zeros wouldn't matter normally, so you can underline it or you can put a decimal there, either one. But you need to know that that zero is important because otherwise you lose its accuracy. So that's temperature conversions in a nutshell. Let's try a density problem to give you an idea of how density can work as a conversion. What's important about density is to know how it works first. So when you think of density, one of the easiest ways to think about it is its definition. Oftentimes you can use a triangle and avoid algebra. Density is mass divided by volume. So I like triangles because you can cover what's you want and you get what's left over. So if you cover D, that's just mass divided by volume. If you wanted volume, you cover V, that's just mass divided by density. If you wanted mass, you could just take density times volume. So triangles work very nice. It avoids a lot of algebra, and any day you can do that, it's a good day, in my opinion. So density is mass per unit of volume. So it's really just how close are your atoms and molecules compared to their volume. So the closer they are together, the more dense they are, the more far apart they are, the less dense they are, and so forth. So if you were to have a graduated cylinder, and you throw in three things, let's say it's water, some gasoline, and some mercury. The densities for those, this is in your notes as well. Gasoline is 0.7, water is about 1, it's like 0.999. And then mercury, very dense at 13.6. So if you throw all three of these together inside, who's going to be where? Well, definitely the biggest density. These are all in grams per milliliter. Going to sink to the bottom. So there's mercury. And then the more dense of the two, water versus gasoline. Water is going to be in the middle, and then gasoline is going to be on top. And that's why oil floats on water, because those are hydrocarbons, less dense than water. So if you were to, let's say, throw in some gold. So you have this gold ring. Gold has got a density of 19.3. How far would it go? Well, it's going to be more dense than everything. This is why they use mercury to separate gold in foreign countries that don't care about the hazards of mercury. It's going to be all the way at the bottom. So there's your gold way down there. And that's because its density is higher than, say, mercury. Ironically, if you throw in lead, which a lot of people think is very dense, its density is only 11.4. So the reason that fishing works pretty well with lead sinkers is lead at 11.4 grams per milliliter, definitely going to sink through water, but, so it sinks to the bottom of the lake. So let's just say here's your little lead fishing sinker. Sinks through water, but it's going to float on mercury. So if you were to go to a foreign planet where they had fish in lakes of mercury, because there's some weird alien fish, now your lead is a topwater lure instead of a bottom dragon lead kind of lure on Earth. And that's how density works by number. If you wanted to do a density kind of problem, using some of these numbers, let's just say we have gold. So gold's density is 19.3 grams per milliliter, based on that chart in your notes. Let's say we have 5.02 grams of gold. What's the volume? To do this, we just cover up V. V would be mass divided by density. So V equals mass divided by density. The mass was 5.02 grams of gold, which is three significant figures. That zero is between two non-zero numbers. Here we have 19.3 grams per milliliter. So notice grams cancel, they're on top and bottom. If you're on the bottom of the bottom, you're really on the top in the sense of units. That'd be great if that's how it worked in real life, but it doesn't. So let's do this in our calculator. Let's see how messy it gets. So turn our calculator on. We have 5.02 divided by our density of 19.3. Notice this is the issue we have in our calculator is we get this gigantic screen full of numbers. This can't be the answer to the problem no matter what. So if we have this answer of 0.260103627, if you circle that answer, there's no help I can give you. What we want is what part of that answer is useful. Well, we have 3 versus 3 and significant figures. We need to keep 3. All the rest of this is just rounding. So the answer is 0.260 milliliters. and that's how you do density. If you needed volume, same kind of idea would work. You could use it as a triangle as well. Volume is length times width times thickness. So if you wanted the thickness of something, which is also sometimes height, you could take volume and divide by length times width, so it worked in the same way, canceling units along as well. The only other major conversion kind of idea in this chapter is heat. And heat is in calories. So let's talk about calories. You probably recognize calories in the sense of food. Those are very different kinds of calories. We'll talk about why here in a minute. But when we talk about heat, we can use a similar kind of triangle. A little bit more complicated than how we set it up. Q is heat. It's in calories. You have mass, specific heat, which comes from a table. Mass is in grams. The table values here are going to be calories per gram times degrees Celsius. And then you have delta T, which is change in temperature. So temperature final minus temperature initial. But this is a great way to practice unit cancellation, unit conversion as well. So if you were to look at that very last problem of your PowerPoint notes, you're going to see a Twinkie. So if you take a Twinkie and you put it in this calorimeter, just a calorie meter, what happens is you add oxygen until it burns completely, releasing all this heat from all the sugars and starches and fats and oils and waxes, all that kind of stuff that's inside a Twinkie. So we put our Twinkie inside, we incinerate it until it is basically dust. We have 1.00 times 10 to the 4th grams of water surrounding the Twinkie and this little bomb cavity that we burn it up and blow it up into. We measure the temperature, so we look for our change in temperature. For this particular experiment, it starts at room temperature, which is 25 degrees Celsius, and it goes to 45 degrees Celsius. And the last thing we need is the table value for the water that is being heated, and that just happens to be the standard that all things are compared to. That's 1 calorie per gram times degrees Celsius, which is a great conversion. This is the specific heat of water. So using all that information, let's find out how many calories are really in a Twinkie. So we cover up Q, which is the calories of anything. So Q equals the mass of the water, the specific heat of the water surrounding the Twinkie that is being warmed by the Twinkie burning, and then the change in temperature of the water because of the Twinkie burning. So using this information, here's our mass. We have 1.00 times 10 to the 4th grams of water. That's what, 100,000 grams, so that would be 100,000 milliliters, so that would be 10 liters of water, so quite a bit. The specific heat is our practice for conversion, so that's 1.00 calories of energy is required to raise 1 gram, 1 degree Celsius. Water has one of the highest specific heats on the planet. It slows up, heats up very slowly, cools very slowly, which is important for our climate on Earth. Notice though, grams cancel, and that's the whole point. It's a complicated problem, but unit cancellation shouldn't be the complicated part. We need calories, so Celsius is left. Go figure, we have change in temperature left. We have 45 degrees, subtract 25 degrees in Celsius. Celsius now cancels as well. So here's the fun but astonishing part. We have 10,000, not 100,000, 10,000 grams. Times 1, which is still 10,000, and then this is 20 when we subtract. So 10,000 times 20, I think I said maybe 100,000, I meant 10,000 earlier. Times 20 is the answer, I just knew the answer before I got to it. 200,000 calories. So you might think to yourself that there's no way possible that there are 20,000 calories in a Twinkie, but this is an actual data from an experiment using a Twinkie, so it's true. 20,000 calories in a Twinkie. But unfortunately, the government tricks us a lot. In this case, the FDA says this number is just too big for us to deal with. So how can we make it smaller so we can make people feel better about themselves when they eat junk food like Twinkies? So they said, well, we could do kilocalories, but because we have so many immigrants, that would just take away 3 zeros and we'd have 200 kcals, which is still the answer if we were to round up. Still be the answer regardless. But most of our immigrants are going to know the metric system. They're going to know that this is still a very large number. So let's just change this completely. Let's just say 200 capital calories, which is still the answer, but it uses a capital letter to hide the fact that it's really a kilocalorie. So when you look on a Twinkie, it's going to say 200 calories per Twinkie, but that's really 200,000 calories total. Still a conversion problem, which was the point of this entire exercise, but it's kind of a funny story that if you have a 2,000 calorie diet, that's really 2 million calories from the metric system. So pretty crazy, but nevertheless a unit conversion problem with heat or density or temperature, doesn't matter. What does matter is that your units cancel always for the next 3 weeks, or you're not going to like them at all. So see you in week 14.